Chris Goodyer from ARM, and I work on ARM performance libraries and also alongside many open source libraries. So in the course of the next half hour, I'm going to give you a brief introduction to how maths libraries kind of work on ARM today, what the options are for you for getting high performance, and what you can do with your applications to try and increase performance. So one of the key things about numerical software is that it's the heart of so much of the HPC systems. And underneath the hood, no matter what sort of application you're doing, there's a very small set of different sorts of algorithms that are done, whether they're matrix style algorithms, fast Fourier transforms, various different things like that fit together to form part of your overall application. They themselves are built up from some high level packages that you may include in your application, which go to successively finer levels. For example, as shown in the diagram, you might be calling some code from PETSI, but itself, it may be linking into LAPACK code, which then calls down into BLAS code itself. As far as these libraries go, on ARM today, most of them just work out of the box, so you should have no problems in terms of being able to compile any of these packages up. Sometimes they need to have specific optimizations to get the highest performance on a particular architecture. And today, lots of those packages already have those optimizations in for ARM, and more are being added all the time. These packages are a mix of both open source things and also proprietary ones. So if you require something like a vendor maths library, we actually have that available for you already. On ARM, the vendor maths library is called ARM Performance Libraries. And this is like the commercial slide that we show to people, the marketing one. At the very high level, we provide interfaces to BLAS, LAPACK, and FFT through very common interfaces. So the FFTW interface is fully supported for fast Fourier transforms. We also add extra interfaces for sparse linear algebra and batch BLAS support. And we'll talk a bit more about those later on. And also we have various high-performing implementations of libm functions, including vector implementations as well. One of the things that as a vendor math library we have to do is to provide high-performing implementations. So these get tuned for specific platforms like the Neoverse N1 cores, which fill the Graviton 2 systems in AWS. And the other part that's crucial for a vendor math library is that we're making sure we give the right answers. So we validate our suite with the NAG test suite, and this is then shipped to you in a way that you can be confident about the results that you're getting. Going into slightly more detail then, what does it mean to say that we're the vendor math library here? So first of all, we provide two different versions. First of all, one is a commercially supported one, so a paid for product, which comes as part of ARM Linear Studio in ARM Compiler for Linux. So this is an LLVM based compiler with integration for ARM performance libraries as well. With that suite, you get both GCC and ARM Compiler for Linux optimized versions of the ARM performance libraries. And you get microarchitectural tunings for all different ARM and partner cores used across HPC systems. We also provide a free version, which is available for download just from the web. This is only compatible with the latest GCCs, so 7, 8, 9, and 10. There's versions compatible with those available for you. And we make sure that we do have microarchitectural optimizations for all ARM designed cores, such as Neoverse N1. So your Graviton 2 systems will work nicely with the free version of ARM performance libraries there. What does it mean to be the vendor maths library? So this is a solution provided by ARM itself, who should have a good idea how to get great performance out of their own architecture. So we're able to work across the stack, whether it's on the BLAS functions, LAPACK, FFTs, or beyond, and we get really good performance across lots of these options. That doesn't mean that the open source alternatives are not also good, and in some cases will beat ARM performance libraries implementations. So it's always worthwhile making sure to find out how your particular application works across these different library choices. Other alternatives on different platforms include MKL on x86 or ESSL if you're on Power. Some system integrators will also provide their own tuned versions for their own systems, sometimes including work on interconnects, for example, Craze libsci. So what is it you get with your vendor maths library with ARM performance libraries? If we think about this stack of operations that we provide, BLAS itself is part of LAPACK, as we saw before. So if you choose an open source alternative such as Bliss, they've got really, really high performance implementations of especially what we call BLAS level 3 calls, which we'll come to later on. OpenBLAS is a slightly more broader product than that, in that they've got more optimizations across the BLAS stack and across LAPACK. ARM Performance Libraries has optimizations at all of those levels. Also, they have high-performing FFT implementations, similar to the FFTW ones, and you'll see that we use the same interface. And also we provide, as I mentioned before, sparse, batched, and optimized libm functions. Now, the libm functions we're talking about, we also provide in open source. So ARM optimized routines is the route we use to actually ship those to customers, so that people can pick them up and build them into their own solutions if wanted. But we provide them through ARM performance libraries as a quick, easy way for them to be linked into your high-performing application. Unfortunately, it's not the state that you can actually just say, I want to have a library which provides all these functions. There's a certain set of choices that you have to make to know which ones you're going to want as well. So the choices that you'll need to consider will be, which version do I want in terms of parallelism? Do I want OpenMP within the library itself, or do I want to have OpenMP within my application? On today's modern systems, we have very large numbers of cores across most ARM devices. So you want to be able to take advantage of as much of that parallelism as possible normally. If you've not written your application to want to use all those cores itself, then you probably want to let the maths library actually do that implementation. So turning on OpenMP will be a good option there to run, for example, your matrix multiplication cases using as many cores as possible. You may also want to use nested parallelism, the idea that you can have some OpenMP in your code and then to be able to allow the library to do extra parallelism inside as well. The second choice you need to know is whether you want to be using 32-bit or 64-bit integers. This is actually very important for whenever you're solving cases where you've got especially big numbers, very large counts of things, which are going to cross into that 64-bit boundary. This is because the BLAS and the LAPACK interfaces are actually written in Fortran originally, which means that everything has to be compatible with what they went for back in those days. So knowing whether the rest of your application is 32-bit integer or 64-bit integer is very important as well. And both of these choices are also important, not just if you're using ARM performance libraries, but also the same if you're using OpenBLAS or Bliss for these implementations. There's also the choice of compilers, which is going to be important to you. What are you compiling the rest of your application up with? Because you should not mix a GCC build and an ARM compiler build. For the most part, these two are compatible, but in terms of these Fortran interfaces to functions that we talk about, there are some differences between the ways that ARM Flang, for instance, handles function return types for Fortran, and GCC handles them differently. So being able to know which of those two compiler toolchains you're using will also mean that you've got the right implementation going into your library. If you choose the ARM compiler for Linux implementation, there are added integration options to enable easy use of ARM performance libraries. For example, we've got the -RPL flag, which can be used at both compiling and link stage. If you're using FFTW rather than ARM performance libraries for your FFTs, then remember that you also need to compile it up separately if you want single or double precision. They are separate compiles in terms of being able to get those. As far as documentation goes, the open source libraries have their own pages, which I'll link to later on. As far as ARM performance libraries goes, we've got full developer documentation now online. So if you go and click there, you can find a full description of the API, including what all the parameters do and need to be passed in, for example. And there are also examples provided in the code when you have a look in your directories to find that you can see how both C and Fortran calling into these functions actually works. And there's also a getting started guide online. So a quick run through some of these APIs then. BLAS and LAPACK. These are quite old interfaces that have been around since the late 70s for the BLAS interfaces. And now they keep being developed, the latest versions up to 3.9 for LAPACK. So how do they actually work? They come in both real and complex flavors in both single and double precision. So each routine typically exists in about 4 precisions. Sometimes there's a few extra complex ones. So there's Hermitian cases as well, for example, in terms of matrix types you may be describing. Beyond that, you can then start to break down the name into understanding what it's doing. So the first character denotes the precision that's being used. So for example, in the name dgem, the D is double precision. The GE stands for general format. So this is all IJ values will exist in that sort of memory space that you're using. There's also other formats such as banded or packed that you may be able to pick up for specialized use cases. And then after those, the rest of the name typically refers to the operation being done. So in this case, MM is a matrix-matrix multiplication. If it was MV, that would be a matrix vector multiplication. So BLAS comprises of about 3 different levels. So vector-vector operations are called BLAS level 1. There's matrix-vector operations at level 2, and matrix-matrix operations at level 3. These differ from each other in that the vector-vector operations are very much memory-bound in terms of how they work, whereas matrix-matrix operations, they are very much compute-bound. So you're able to achieve much higher, closer to peak performance for your implementations. In total, we've got about 156 BLAS routines, which are there to provide these really high functional building blocks, so super optimized to make sure that when you're calling into them, you get the best performance. The next step up the stack is LAPACK. So this is used for a wealth of different problems, whether it's solving matrix equations or eigenvalues and things like this. Again, Fortran interfaces. Both of BLAS and LAPACK are callable from all languages. So there's CBLAS and LAPACK-E interfaces as well, if you're calling from C or C++. And we do exist with the latest versions of LAPACK available. So 3.9.0 is the one that's around in our performance libraries 21.0. And there's an awful lot of LAPACK routines. So these are built on the BLAS routines to make sure that high-performing implementations for the bits that really do that hard work does keep coming. One of the very important parts about BLAS libraries is that they are really high performance, as I mentioned. So that means having written them in assembly code, typically handwritten assembly code, in order to maximize the overall performance that you can achieve from your application. Because of this, you really need to understand the microarchitectures that you're writing it for. And that means that writing for a different core, a different platform, will mean you need to use different instructions or different orderings of instructions. And this is something that all the BLAS implementations do, whether it's OpenBLAS or Bliss or ARM performance libraries. For the open source libraries, you need to have made this choice beforehand when you're compiling your library up to make sure it's optimized for the right platform. Whereas for ARM performance libraries, we've actually put some technology into the library itself to enable automatic switching at runtime to make sure you're picking up the highest performing implementation. As you can kind of see on the right-hand side, the overall performance between BLAS, LAPACK, and Bliss is always very high for most cases. So for areas where they've really optimized areas, for example, dgem, that very common benchmark people use for marketing purposes, this is showing a case running at 64 threads. And you can see for very large cases here that we're all achieving pretty much the same performance, which works out at well over 95% parallel efficiency based on the serial case. However, you can also notice there are some differences, especially around smaller problem sizes, as to the performance between the libraries. dgem is a very highly optimized case that exists on these platforms. So it can be good in terms of seeing the overall performance of your system, but not necessarily always going to be representative of what your application does. So different libraries will have optimized slightly different areas. So do have a look at the different choices to see how your application overall performs. One area that ARM Performance Libraries has added that I haven't seen yet in OpenBLAS or Bliss is half precision implementations. And for example, on the full 64 threads of Graviton 2, we're able to achieve over 4.5 teraflops worth of half precision performance for a matrix multiply. Fast Fourier transforms are another very common part of many scientific applications, whether this be signal processing things used on small devices, up to real science codes looking at molecular modeling and quantum physics interactions and things like this. So the way it typically works is you do a planning stage first, which does a bulk of the time in terms of preparing what the best way of solving the problem will be. And then later on, you can execute this plan many times and be able to take advantage of having done slightly more work to start with to be able to get fast execution later on. FFTW's interface, the FFTW3 interface as it's known, has become the de facto standard across scientific applications. And so ARM Performance Libraries does implement the full set of transforms here that FFTW3 provides. That means 1D, 2D, 3D, and multiple dimensions are all provided in complex to complex, real to complex, and complex to real forms. There are also discrete cosine transforms in FFTW as well. These are also known as real-to-real transforms, and these are also now supported in ARM Performance Libraries since the 21.0 release. And ARMPL also provides single, double, and half precision. So again, an extension to the FFTW standard in case you were wanting to get some even faster but less accurate versions, for example, in machine learning cases. ARM Performance Libraries also supports the MPI interface, which FFTW provides, and we make sure that rather than shipping code for each one of these implementations, we're actually generating those at planning stage using a JIT compiler to enable a smaller size of download package and with no impact on performance. In terms of being able to compare ARM Performance Libraries versus FFTW, the graph here kind of plots the two against different lengths of transform. And for FFTs, it is really all about the length of transform that matters. This is because it's the FFT is broken down into its prime factors. So whether you're solving small problems or large problems, it is very different to solve a case of 60 compared to 61, for example. What we can see in this graph is dots above the line are cases where ARM Performance Libraries is faster than FFTW, and dots below the line are where FFTW is faster. So typically, apart from some very small cases, it's very much the case that you can see an advantage for ARM Performance Libraries on the Graviton 2 processors here. And these are just one-dimensional profiles. If we go into 2 and 3 dimensions, you'll see that this performance advantage typically extends further. Sparse matrix support is one of those extensions that we've added into ARM Performance Libraries. This is because there is no single standard that people like to use for their sparse matrix support at the low-level sort of implementation level. Doing a CSR, for example, is very common for sparse matrix vector multiplications. So we use this as our reference code. But we also know that going beyond a CSR implementation is also important. In cases where you know that you want to reuse your matrix multiple times, by being able to take that knowledge in to start with, enables us to optimize this matrix better before it's used, and then use that operation multiple times on this optimized object. The graph on the right shows the performance of our optimized version here, allowing reuse over the one where we just do our basic CSR implementation. So you're looking at 50 to 100% improvement typically in performance. And this set of matrices is taken from the sparse matrix suite. So there's a real range from very small to very large cases. Batch BLAS and batch APAC interfaces are also something that is growing in importance for many codes. This is the idea that you don't just want to solve one matrix multiplication, for example. You might have a very large set of them that you're wanting to be able to take advantage of. One of the disadvantages of a library like BLAS is that every single time you make a call to it, you have to do some checking of the input parameters. For most cases, this isn't a problem. But if you're just doing 2x2 matrices quite a lot, that overhead can actually add up to being something significant. So what you can actually do is to be able to skip that stage and say, I want to solve 1,000 of these cases. And you do that using the gem batch interfaces that we provide. Even higher performance is possible if you know that you're going to be reusing the data that you've put into these formats more than once, or you're actually controlling this data through your own pipeline, and you have control over where the data goes. And this is for what we call our batched interleave processes. So in this case, rather than having the matrices separately in memory, we allow them to, through a call, to be interleaved in memory to enable us to have multiple batches with however many matrices interleaved. And this then allows extra optimizations to be done. The graph on the right here shows DPOT-RF, so this is Cholesky factorization, comparing the batch interface against what you'd normally get by just having a loop over the LAPAC code. And you can see the massive increase in performance by allowing interleaving of these functions. We've got quite a lot of functions already supported through this sort of interface, and if there are more that you think should be added, do get in contact and let us know what would be useful for your use case. As I mentioned before, we have this extra library which looks at optimized libm functions, which we call libamath. And similarly, we have libastring for string functions as well. What we're trying to do here is to try and improve on the performance that you can get out of your standard -lm flag that you'd put on your standard Linux system. So we've been working for several years now to make sure that, to start with, we can take better implementations that we've developed ourselves. First of all, get them open sourced through ARM optimized routines. And secondly, get those upstreamed into places like glibc to ensure that Linux distros can actually be able to pick those up as well. On top of that, though, we want people to be able to get access to these higher performing implementations today. So through ARM performance libraries, libamath gives you that option to be able to pick up higher performing implementations of things like trig functions, power functions, error functions, making sure that we've got quite a few of these massive speedups that you can actually obtain, even for scalar computations. On top of that, if you're able to use ARM compiler for Linux, the options there to be able to get vector implementations as well. Unfortunately, that's not possible through GCC today, but by just adding the -rmpl flag to your ARM compiler for Linux build, you'll be able to pick up those sorts of high-performing implementations. In terms of how you go about using ARM performance libraries then, if you've already set up your code to use a different BLAS library, maybe on a different architecture, if you're calling into BLAS, LAPAC, or FFTW, then the standard APIs will just work and you shouldn't need to change anything. If you want to do any sparse or batched operations, you'll need to add the appropriate calls into your code. But in time, if these become more standard, we would look to be adding these standard codes in as well. For using FFTW's interfaces, again, that just comes through the standard header file. However, if you want to use the MPI interface, make sure you're linking in our FFTW interface rather than the FFTW provided one, because there's some magic that happens for the MPI cases there. And regular header files, if you've got like blas.h in your code, that will also work and link through to the right functions that we're providing to. And modern Fortran, if you want to use a module to get access to those things, it's use ARMPL library as the way you get access to these codes. Once you know how your code's written, you then need to go about linking in the correct library. As we mentioned before, they've got the choice between serial and OpenMP builds, and you've got 32-bit and 64-bit integers. This basically means that you've got 4 different libraries that you're wanting to link in yourself, one of these options. So LP64 and ILP64, these are the difference between the 32-bit and the 64-bit integers. And the _OpenMP adds the OpenMP builds, the _MP adds the OpenMP builds into your library as well. So those choices are provided there in both static and in shared form. And then when you come to compile up, if you're using GCC, you need to put the -i in the include directory, or the and the -l and the library directory to pick up the library versions you want. And as we mentioned, if you're using ARM Clang, just minus ARMPL will, on both of those lines, will do the same job for you. If you're linking in ARM performance libraries, libamath will automatically be linked in for you. But as I mentioned, vector calls will only be available from ARM compiler for Linux there for you. If you're doing this via SPAC, there's slightly more machinery you have to go through, but you're providing the same choices once again. So through SPAC, you have the idea of a virtual package. So we have these, for example, to provide things like BLAS and LAPACK. And different packages themselves will say what they're providing. And then you can have a choice that is defined at the installation time, but you can then choose to use a different one, for example. So if we were looking at these, for example, we're asking for SW4 Lite in a GCC version, and that's the output that we get from this spec output. And you can see there the highlighted section says we're picking up ARMPL 21.0's implementation, but with GCC 10. If you put the hat open BLAS on the end of the same line, rather than ARMPL, you can see that you've picked up the open BLAS implementation. And yes, it's a much longer name, but all you have to remember is the hat open BLAS for getting the right bit to go into your code for that part. In terms of what sorts of implementations can you pick up, there's a very long list available inside SPAC for the different packages, but obviously not all of these will be available on all platforms. So if you're on an ARM system, there's a smaller set than if you're on an Intel system. And how do you go about using these virtual packages then? So we've got each of these libraries wrapped up with providing what's there. So if you know what's going to be happening, you have to, it then adds the target flags that need to go in there. And so it knows inside that package what extra libraries need to be linked in. So for example, you can see we've linked in libarmpl. Because of the way SPAC works, it's better to actually hardwire some of the other libraries that it links in as well, since LD library paths aren't used. So amath, astring, libm, libgfortran, for example, they're all linked in by default through the SPAC way of doing it, where normally you wouldn't have to do anything to pick those ones up. And then how do you go about choosing which of the different variants you want? So quite simply, and this is across the packages, you can do threads equals OpenMP if you want to pick up the OpenMP version, or the 64-bit version, you add a plus ILP64. So there's defaults for what you get if you don't ask for something, and then you can ask for something beyond. So if you like looking at the two examples at the bottom of this thing, if you're saying this depends on ARMPL plus ILP64, threads equals OpenMP, you've got the ARMPL version there, or when it's Open BLAS, you can ask for the ILP64 version and OpenMP in the way they're defined as well. Okay, so that gets you all up and running and using the libraries and being able to write your code. Now, the next question is, how do you know what your code's actually doing in terms of recording data? So what we've developed is an open source library called perflibstools, which you can just get access to through the ARM software GitHub. It's a free download and it should hopefully be useful to you, but it definitely, if you can share some output data with us, it's always useful to us too. This enables us to get a real breakdown of what sorts of calls are going on inside your libraries to work out where the time is being spent, and to also able to understand whether you can make any optimization codes to your code by seeing a strange pattern in terms of where the accesses are. So there's various pictographic representations that you can get out of this. For example, the bar charts on the right showing where either number of calls are being spent for the top three things between BLAS level 1, 2, and 3, or time being spent on the bottom three there. And we also have heat maps which describe how the actual dgem cases called, for example, are split between different transpose types and also problem sizes. So that's orders of magnitude going up each of the axes there, with white indicating a large number of cases in those areas, and then cooler colors indicating less cases with those sizes. So we've actually used this quite a lot in terms of our own optimization, especially when we've had performance questions that we couldn't quite answer ourselves. So one of the first things we were doing many years ago was looking at OpenBLAS versus ARM performance libraries on the HPL benchmark. And we were seeing that there was a performance hit which we didn't quite understand. So we're starting to look at some of this data. We can see the pie chart at the top. That indicates how the number of calls going on there. And you've got ARM performance libraries on the left, OpenBLAS on the right. And you can see the number of calls that are split the same between ARM performance libraries and OpenBLAS, between the NN and the NT transpose cases. However, the bottom pie chart shows the time spent solving each of these cases. And you can see that at that point, ARM performance libraries were spending a lot longer solving the NT as a proportion of the time than OpenBLAS was doing. We then looked at the pictures on the left, these heat maps, and we're able to see some red squares in the ARM performance libraries plots where we weren't getting them in the OpenBLAS ones. And this was able to point out some very large overheads that were in there for very small cases. By fixing those, that was able to then fix the HPL performance to enable us to at least achieve as good a performance as OpenBLAS, if not better. So how about going about using this? Nice and simple, just git clone from GitHub for you, cd into the directory. If you want to change it from using ARM Clang to using GCC, just edit the makefile before compiling it up. Then you just set LD preload on the library that you've just built to enable you to collect some sort of summary data. And then assuming your application has got a shared version of ARM performance libraries or OpenBLAS or Bliss or one other implementation linked in, then just run your application. And at the end of the run, you'll get a line printed out that tells you where the output summary data has been stored. So this output file is a basic text file summarizing all the data that's been collected. So it lists all the calls that were made, the number of times that call was made with those parameters, and also gives you some idea of how long these actual processes took. This is then able to be used for post-processing in a variety of different ways. I've already shown you some of the pictorial tools that we provide. We also provide some text-based tools as well, which offer even more information. So for example, the process summary one is about the finest level of detail for most cases that are needed here. It tells you the number of calls into each of these different sorts of levels that went on, and also the time spent doing this. So in this particular case, you can see that the largest proportion of time was spent in BLAS level 2 calls at 1,672 seconds. It then breaks down this information further, telling you which calls themselves were actually being spent to actually provide this time. So looking at the BLAS level 2 section, you can see that of these 1,672 seconds, all bar less than one of them were spent doing DGMV cases, which is quite interesting. Ordinarily, we wouldn't be surprised to find DGEM cases at the top on the right were the largest uses of time, but in this case, they're like 2.5 seconds. So this could be an area where you as an application writer could think, actually, could I do better here? Could I transform from a DGMV case, which is pretty much memory bound in terms of getting access to all these vectors, to actually something that's compute bound? Could I rewrite all these vectors as a single matrix that I could multiply together to get the right sorts of performance that I'm interested in? Another case where we were able to learn something useful was a user reported to us that when they were compiling up their application, using us as the implementation of the BLAS functions, but FFTW provided by Cray as the implementation of the FFTWs, they got faster performance from FFTW's cases rather than ARM performance libraries. And in this case, you can see that the BLAS difference here, ARMPL was faster than OpenBLAS, but we're talking a couple of years ago for this case. So we were really intrigued as to know why we were like 15 seconds slower in terms of solving these FFT cases than FFTW was. So we ran some perflibs tools, or the user ran the perflibs tools and provided a lot of data to us. And as part of that, we could actually start to get the sorts of breakdowns we were interested in. So on the left, you can kind of see which calls they're making and the lengths of the FFTs that they were solving. And we looked at those and thought, hey, but we should be faster on those cases than FFTW. And then the execution time on the right, we were able to compare the output from ARM performance libraries to FFTW and also see that, yes, indeed, we were solving them faster. However, when you look at this table down the bottom, you can see that we were doing the executions faster, but the planning stage was taking a lot longer. Now, the reason for this is actually also indicated on this table. If you look at the top, you can kind of see the number of times that the planning stage has been done. So 20,000 plans have been made and executed 24,000 times. So that's pretty much one plan per execution in this case. And as you'll recall before, the idea is you plan once and you use this plan many, many times, whereas this application did not work in that manner. So it was planning, using, destroying the plan each time. And whilst we should actually be able to hold on to lots of data through wisdom, and we were doing that, there was also an unnecessary overhead where we were zeroing an array which didn't need to be zeroed each time at planning stage. This was therefore a very quick fix, and within a week we were able to turn around a solution and get that out to the customer. And more importantly than that, though, this was able to reduce the time for solving the problems. So the graph on the right shows the performance before, the 18.4.2 line at the top. This is time per iteration. The green line was the FFTW time, and the blue line was the 19.0 release. So that one simple use case where a person writing the application hadn't quite appreciated the steps that the library would be doing, and we hadn't appreciated that a library would be called in that manner, we were able to make the change, to make the improvement, to get a real massive step change in performance for the actual cases they were interested in. Okay, that's been a nice quick tour of quite a few of these open source products. There's lots of information on the web for you. So ARM performance libraries, full documentation, and the getting started guys on the web, as I say. You can download Perflib's tools from the GitHub site, and we are really keen that you do be able to share data with us. As much useful data as you can give us as possible. This helps us both with prioritization of our work, and also, as we mentioned, can help you identify where you can do better in your codes. OpenBLAS, Bliss, and FFTW, they've all got communities you can access online if you need to report bugs or ask questions there. But first of all, if you're taking part in this AWS ARM HPC user group hackathon, do ask on our Slack channel, the Help Math Libraries. We've got plenty of people that should hopefully be able to help answer your questions there. Thank you very much for listening. Hopefully this has been useful for you, and good luck on building your applications on ARM.